Hello, my name is Nathaniel Madrigal, and I'll be going over Code Review 5 Dependent Weighted Random Query with Colors using KDTree. We will cover the KDTree class we made. This one it does a dependent weighted random query similar to Code Review 2, but unlike it, it's using a multi-dimensional KDTree instead of a one-dimensional range tree. And we'll also be going over how we made it scalable for different dimensions. So here is our KDTree class. We have just a declaring constructor, and then the main thing is that it calls this function build KDTree. That's going to be actually building the KDTree structure, and then I'll go over that later. But first, I'll go over what is a node that we define in this KDTree. So a node has a list of coordinates, so that's what we call the coordinates, and then it also has the color associated with that coordinate. So has a color and coordinates, and this can depend. The size of coordinates can vary depending on the dimension. Left, right pointer, box, which is usual for KDTree, but two different things dependent compared to independent query is we have a key and max node instead of a weight. And then we'll see how it is in KDTree, but this allows us to do, this is what makes it dependent. A bounding box, so where this is this is box right here, that will be a bounding box struct. And here it's just a box with min coordinates. So for every coordinate, the min value, and for every coordinate, the max value. So that's how it contains a box. So here, we'll be looking at the first function or method, build KDTree. It is it's a normal KDTree. So most things are normal. This one is just if the depth is, or if these are none, which it'll first call none. It sets depth 0, initialize it, and then here it will just parse through the data and find it'll find the minimum coordinates for every dimension and the maximum coordinates for every dimension. So it has a bounding box that defines the entire data set, the root. And then here we have the base case, which is if we're just looking at one node, how will we define it? So here we set the box, and here's where we go into the key. So here is the formula for a key, where it's just a random number from between 0 to 1 to the power of 1 over the weight of that. And we get that weight from a dictionary we passed through this function. So this is how we have a color dictionary. And then that key will be a random number, and then that number, the way this dependent does it is it will look for the highest key, and it's a random one, and then we say that picking the greatest key is equal to randomly choosing that node. And then max node here is it will store if it had children, if this node had children, which it doesn't, it's a leaf. It would store which of its between itself and its children, which has the highest key, and it'll store a pointer to that. And because it's only a leaf, it'll store a pointer to itself. The recursive case, here we have where it'll change the dimension depending on the depth, normal KDTree stuff. Here it'll sort the data set, it will find the median, it'll split it into the left and right side. So the left would be you'll point to the left pointer, the right pointer. Here it defines, it'll set the coordinates, because we have a box for which we found here the initial box for the node, but you have to find the box for the left node and the right node. So here it finds the left box and right box, and it's basically the same box. The only difference is that the left box, its max coordinate on the dimension it's currently at will be the median, and then the minimum coordinate of its current dimension will be the median. And then, yep, and then here's the actual recursion where we call, say, this node's roots left is build KD tree, and then build KD tree, box left, box right, and then on the data set left and right. And then here's where we assigned, now we actually made the left and right. Here's where we assign what the values of this node is, this root node. So we look at the left and right key because we're inferring based on recursion that we'll eventually get to leaf nodes. So this will call when we actually hit a leaf node, because the keys are calculated on the base case. If we're going to see if the left key or right key is higher, and whatever is higher, we set the roots key to that key, and then we set the max node pointer to that whatever we chose. So if we chose the left, it'll make it the left. If we chose the right, it'll make it the right. That way, so if you think about it, if you have like left and right, which is like let's say 0.2 and 0.5, the root will have 0.5 and point to the right. So that way it stores the max values, and then over the entire tree, it will keep on climbing up, finding the maximum. And this is why it's dependent. So if you had, we say choosing a random query, it will just choose the max. So if you do the same query over and over again, the max will not change. So it's dependent on the range you're giving it. So partition and sort data set, this is a quick sort implementation just to sort it, to sort the list, which we did in the recursive case here. Yeah, query random sample. This is what you're actually going to do to query a node. So we have this function find canonical nodes. I'll go over that later. But if you know, like a normal KD tree will find the canonical node, all the canonical nodes, which means given a range, give me all the nodes or points where itself and its children are part of that range. And then it will run just a simple formula. It will try to find the canonical node with the maximum key. And then when it finds that canonical node with the maximum key, it returns the max node. If you remember, a max node is a pointer to one of the leaves. And then so it will return one of the data points. That is the max. And then how do we actually find the canonical nodes? This one is no different from a normal KD tree. Yeah, normal KD tree algorithm. So the first case you want to check is if it's a leaf. So you're gonna give it a range, and then you're gonna give it a root to look at. Actually, it assigns itself. It's the root because the class stores a variable of what the root is. So we'll just look at that. But it will, yeah. So it's gonna first check if the base case, which is it's a root. The root you're looking at is a leaf, and it's just a very simple. It's just going to check straight up if the coordinate of that is between, like in this case, is the coordinate less than the min, or if the coordinate is greater than the max. That means it does not. The leaf does not intersect with the range you're giving me, and then it'll just break. And then here, so if this is like just some boolean, and then if the coordinate, we say that this coordinate intersects, we append it. So here we have a list C. So this is what we return, but it's defined initially empty, and then we just append nodes to it when we find it. So we're gonna append that root. and then else we just return an empty list. Okay, so if it's not a leaf, we're going to look at this case, the recursive case. Well, actually, this is not the exact recursive case, but one of these is a recursive case. So the next step is checking if because now leaf is just a coordinate, but if we're looking at an internal node, that internal node has a box to it. So now we have a box that we're looking to query and a box represented by a node. So we don't know if that box represented by the node is inside of the range we're querying, if it partially intersects the range we're querying, or it completely misses it. So if it completely misses it, like it doesn't, there's no intersection, we just return an empty list. If we do see that it's fully intersects, like the box represented by this node is completely inside of this query range we gave it, it's going to append it. And what we say, if it doesn't completely not intersect and it doesn't fully intersect, it has to partially intersect. So in this else case, partial intersection, because we don't know, we can't do much with that information, it's just going to pass it to its children and then run recursively run find canonical nodes. And then there it'll break it down. And then this right here, just because we're working with lists here, we have to, if there's some canonical nodes on the left side we find, it's going to add our C, which is the one we want to return, to the C left. And then if we have anything on the right side, it's going to add C to that. So then return C, it will return a full list of all canonical nodes. That's about it. It's not much different than code 2, just being a KD tree and being able to scale on any dimension we want. So 2, 3, 4, etc. Okay, that's it.